So, back in 2015, three researchers put out a paper in the journal Nature. And look, it wasn't some flashy discovery of a new particle or a cure for a disease. It was what's called a review paper, basically a summary of a field that was just about to explode. Those three researchers, Jan LeCun, Yoshua Bengio, and Geoffrey Hinton, we now call them the godfathers of AI. And that paper, well, it pretty much became the Bible for a whole generation of engineers and scientists. Okay, let's really get into this.
So, how do you even measure the impact of a scientific paper? Well, one of the best ways is to look at citations. That's how many times other scientists reference it in their own work. As of right now, this deep learning paper has been cited over a staggering 60,000 times. To give you some perspective, that is one of the highest citation counts for any paper in any field in this entire century. This isn't just an influential piece of writing, it's a foundational text for the world we live in today.
And that, right there, is the big question we're tackling. What was actually in this paper that made it so important? I mean, it didn't introduce a single brand new invention. So what was the secret sauce? Well, what it did was provide the first clear, unified vision for the technology that now powers, well, pretty much everything, from the phone in your pocket to the cars that drive themselves.
So here's how we're going to break it down. We'll look at how these systems think in layers. Then we'll check out the engine that actually powers their learning. After that, we'll get into why this paper was such a landmark synthesis at that specific moment in time. And finally, we'll trace its incredible legacy right up to the AI of today.
Okay, first things first, the paper is called Deep Learning. To really get what this is all about, we have to understand what that word deep actually means. And it all starts with a concept that's, believe it or not, been around for a long, long time. The basic building block of all this stuff is the artificial neural network. The easiest way to think about it is as a really simplified model of our own brains. It's just a bunch of interconnected nodes, you can call them neurons, that all work together to spot patterns in data. You've got your input layer where the data comes in, an output layer where the answer comes out, and sandwiched in between you have these hidden layers that do all the heavy lifting. And get this, the wild part is that this core idea isn't even new. This image right here is from a 1989 paper by Jan LeCun, one of the authors. A network is considered deep if it has more than one of those hidden layers. That's literally it. Deep just means you're stacking multiple processing layers, one on top of the other, which lets the network handle way more complex problems. Okay, so the really crucial part is what these layers are doing. The paper explains it perfectly. Deep learning models learn representations of data with multiple levels of abstraction. So what on earth does that mean? Let's use an example. Say you show the network a picture of a cat. The first layer doesn't see a cat, no way, it just sees a bunch of raw pixels. But the next layer learns to spot simple things in those pixels, like edges and corners. The layer after that might combine those edges to form more complex parts, like an eye or an ear or some whiskers. And then finally, the output layer puts all those recognized parts together and goes, aha, that's a cat. Each layer builds a more abstract, more sophisticated understanding than the one before it.
All right, so having layers is great, but how do they actually learn to recognize those edges and corners and ears in the first place? They're not programmed to do it. They need an engine, right? A process that lets them get smarter over time. And that brings us to the real magic of how these networks actually learn. Well, the engine that drives all this learning is something called backpropagation. Imagine you're trying to teach a toddler what a cat is. You show them a picture of a cat and they shout, "Dog." You'd say, nope, not quite, that's a cat. And in their little brains, some connections adjust. Backpropagation is basically the mathematical version of that. When the network gets an answer wrong, the algorithm literally works backward through all the layers, figuring out which connections were most responsible for the mistake, and then it just nudges them in the right direction. It's an incredibly powerful way to learn from your mistakes. And really, this is what it all boils down to. The whole process is about one thing: optimization. That mistake we were talking about, it's measured by something called a loss function. You can just think of it as a wrongness score. The entire goal of training a network, using backpropagation over and over again, is to tweak all those internal connections to get that loss function, that wrongness score, as close to zero as possible.
Okay, hold on. If all these ideas, these deep layers, and this backpropagation thing have been around for decades, what was the big deal in 2015? Why this paper at that moment? Well, the answer isn't about a new invention. It's about context. It was less of a discovery and more of a declaration that a revolution had in fact already started. The absolute genius of this paper was its timing and its clarity. See, by 2015, we'd hit this perfect storm. We finally had the massive computing power and the enormous data sets needed to make these old ideas work on an incredible scale. But the field was kind of a mess, fragmented and confusing. What LeCun, Bengio, and Hinton did was provide the synthesis. They gave everyone a clear, unified overview, explaining why this stuff was suddenly so powerful, and created a shared roadmap for everyone to follow. And this timeline, man, it just lays it all out. The journey started way back with LeCun's work on recognizing zip codes in the 80s. In the 90s, we got new kinds of networks for handling text. But then, boom, 2012. That was the shot heard around the world for AI, when a deep neural network totally crushed the competition in the ImageNet challenge. That's when everyone really started paying attention. The 2015 paper was the culmination of all of it, the moment the pioneers themselves stepped up and basically explained to the entire world what had just happened. So, how do we get from that 2015 paper to the crazy AI we're all using today? That paper didn't just explain the present. It pointed toward the future. And that future, well, it arrived a lot faster than anyone expected. The 2015 paper talks a lot about things like recurrent neural networks, or RNNs. They were the best we had for processing things in a sequence, like text. But they had this one big problem. They read like us, one word at a time. This was super slow, and they'd kind of forget the beginning of a long sentence by the time they got to the end. That foundation, though, led directly to the next giant leap. Just 2 years later, the transformer architecture arrived and completely changed the game. Instead of reading word by word, it could look at the entire sentence at once. This was a massive breakthrough in speed and power, and it's the architecture that powers models like ChatGPT. The absolute magic inside the transformer is a mechanism called self-attention. It lets the model look at an entire chunk of text and for every single word, figure out how important all the other words are to its meaning. Think about a sentence like, "The robot picked up the ball because it was heavy." Easy for us, right? We know it refers to the ball. Self-attention is the mechanism that lets the AI figure that out instantly by weighing the relationships between all the words at the same time. Okay, now don't let the math here scare you. Let's just focus on the core idea. This formula is the engine of self-attention. The simple version is this. For every word, the model creates a query, which is like asking a question, a key, which is like a label on the word, and a value, which is the actual substance of the word. This formula is just a super efficient way for every word's query to check against every other word's key to find the most relevant connections. It creates this incredible, complex map of relationships, which is how modern AI understands context and nuance so well. So when you look back, that 2015 deep learning paper wasn't just a review, it was a catalyst, it was a signpost. It took decades of messy, brilliant research, captured it at its breakthrough moment, and laid the groundwork for the next explosion of innovation, the transformer. It synthesized one revolution, and that just leaves us with a huge question. As AI keeps evolving at this mind-bending pace, what's going to be the next great synthesis? What will be the next paper that helps us all understand the next revolution in intelligence?